counting chips, which are a non-proportional and exchangeable model. Non-proportional because if the yellows represent the ones and the reds represent the tens, they are represented by objects of the same shape, colored chips of the same shape. So these chips require you to set values, like I said, ones, tens, hundreds, thousands, and are best if used with a place value chart like this one. Hi, today we're going to be talking about colored counting chips, which are a non-proportional and exchangeable manipulative. They are non-proportional because all of the place values are represented by the same size chip, so it is difficult to see that a 1 or 10 ones comprise a 10. They're exchangeable because when you have 10 ones to be represented as a 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you have to physically exchange all of the ones for a 10 and remove them from the page. This manipulative is best used with a place value chart where each chip is assigned to a different place value. For the purposes of our demonstration, the green will be correlated with the thousands, the blue will be correlated with the hundreds, the red will be correlated with the tens, and the yellow will be correlated with the ones. There are a number of uses for these manipulatives. Starting with the lower grades, they can be used to count single-digit numbers, 1, 2, 3, 4, 5, 6, or to make patterns, yellow, red, blue, yellow, red, blue, yellow, red, blue, and so on. They can also be used very easily to model addition and subtraction, which we will be demonstrating later in the video. In upper elementary grades, they can be used for tasks such as counting money if you don't have actual currency to model a problem with. For instance, the value of a quarter could be assigned to the yellow, the value of a dime could be assigned to red, the value of a nickel to blue, the value of a penny to green, or vice versa. This manipulative can also be used to learn sorting at the elementary levels. For instance, you could sort by color.
So this manipulative can very easily model numbers. At first, we'll just start with modeling a single-digit number such as 3. Using our chart that we have here, 3 would be demonstrated by placing 3 yellow chips in the ones column. 1, 2, 3. To model a larger number such as 17, we would place 1 10 in the tens column and 7 ones in the ones column. 3, 4, 5, 6, 7. So this is representing 17. To model an even larger number, such as 628, we're going to start using the blue chips. So since we have 6 in the hundreds place, we'll need 6 blue chips. 2, 3, 4, 5, 6. We have a 2 in the tens place, so 2 red chips. And an 8 in the ones place, so 8 yellow chips. 7 and 8. To model an even larger number, such as 1,324, we're going to be using a green chip for the thousandths place, 3 blue chips for the hundreds place, 1, 2, 3, 2 red chips for the tens place, and 4 yellow chips for the ones place. So that's 1,324.
So we can use these chips to model simple addition problems such as 15 plus 4. So we would have 1 in the tens place and 5 in the ones place to represent our 15. And then if we are adding 4, we can add 4 more ones and see that 15 plus 4 is 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And we can do the same thing with simple subtraction. So for instance, 17 minus 6, we would again have 1 in the tens place, then 7 ones to represent 17, and then stop, we don't have enough. And this manipulative can also be used to solve more complex addition numbers that require us to carry in the tens to hundreds place, such as 151 plus 62. So we're going to start with modeling 151, and then we're going to add 62, which means we need to add 6 in the tens place and 2 more in the ones place. So now we see that we have 11 chips in the tens place, and because we know 10 ones is equal to 100, we can pull off 10 of our reds, which is going to bring us to 100, and we can exchange it for 1 blue chip and get that our answer is 213. And for more complex subtraction problems, we can use this manipulative to demonstrate the regrouping process by exchanging our higher place value chips for a lower place value chip. For example, in the problem 127 minus 54, we're going to start by representing our first number, 127. And then to take away 54, we start by 1, 2, 3, 4 ones. And then when we get to our tens, we see we can't take away 5 tens from 2 tens, so we exchange our 100 chip for 10 tens. And then we can take away our 5 tens, which is 50. So 10, 20, 30, 40, 50. And we are left with our answer being 73. So we can also use our chips to model simple multiplication problems. For example, if we wanted to do 3 times 4, we could pull out 4 groups of 3 ones chips and then figure out that that shows us that 3 times 4 is 12, and because this is an exchangeable manipulative, we can pull off 10 of our yellows and exchange it for 1 tens, and then that would be 10, 11, 12 is our answer to 3 times 4. So we can also use it to solve simple division problems. So for example, if we had 100 and wanted to divide it by 2, we would simply exchange that 100 for chips, for tens chips, and then to divide by 2, we would start by splitting them equally into equal groups and see that 100 divided by 2 is 10, 20, 30, 40, 50.
As with most manipulatives, there is a drawback to using the colored counting chips, particularly for modeling addition, subtraction, multiplication, and division. As I mentioned earlier, because they are a non-proportional manipulative, it is not very simple for a student to see that 110 is representative of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ones. So it does require a more abstract way of thinking to understand the depictions of simple mathematics.